Good morning. I'm Jaime Marian. I'm a professor here in the Material Science and Engineering Department at UCLA, which usually means that I always have excuses not to be part of the long program all the time. So you'll see me popping in and out, but it's hard to evade all the responsibilities that when you're not able to leave campus. But I'm very happy to be here. And I appreciate the invitation by the organizers of the workshop. And what I thought I'd give you today is a sort of a perspective on the challenges that we face when designing and testing, simulating, and certifying materials for fusion energy in a general sense, and also try to discuss and identify the mathematical challenges and the computational challenges that we face in developing some of these models, some of these protocols, and validation and testing benchmarks that we design for fusion materials. All right, so feel free to jump in and ask questions or make comments as I go. In my mind, there's no need to have it in a formal way. Just raise your hand and we can just have a discussion as I go. So if there's something that you want to comment on or you need more clarification on, just please jump in and feel free to do this. Okay. So the first thing I'm going to do is I'm going to give you a brief overview of the environment under which fusion materials will have to perform. And that'll set the stage for some of the challenges that I'll introduce later in terms of material simulations and material certifications and things like that. Then after that, we'll go into a little bit of the fundamentals of irradiation damage theory, which is more or less the theoretical context within which we have to design and develop our models. And then I'm going to basically walk you through a couple of designated examples that are relevant for fusion energy. And then we'll see how these tools and these models that we develop are deployed in a specific case. Okay, I think it'll make it easier to understand and see how these things go. Yeah?
Can I ask you what DPA means?
You can, and I have a full slide devoted to that. So we're going to get there. But it stands for displacements per atom. And we'll go into, Man, you're good. Like, usually people wait until I get to that slide and there was some DPA in there. Yeah, good catch. All right, so let's talk a little bit about what fusion materials, specifically structural fusion materials, are going to be facing in a fusion operational scenario. So generally, use the pointer here. So generally, when you ask, and this is true of students, undergraduate students and graduate students, but if I say, tell me in your mind, and you don't have to be a materials person for this, but tell me in your mind, what would be the most severe materials degradation process that you can think of? And some people would say, oh, it's going to be fracture, or it's going to be corrosion, or hydrogen embrittlement, or irradiation, or ultra-high temperature, ultra-high deformation rate, something like that. In fusion, we have it all. Like, they're all co-operating at the same time. And I'm not being dramatic. We have issues associated with mechanical stress. We have issues associated with a highly reactive chemical environment. We have issues associated with atomic displacements. This is directly derived from high energy radiation. And finally, we have issues associated with transmutation. This is nuclear physics. So you can see, and I'm not going to go through all of these, but some of the associated effects of all these issues. But stress, you're going to have a relatively large component, which is a load-bearing component. So it's going to be subjected to stress. In addition to that, it's going to be facing cyclic stress, very, very intense thermal stresses, whether you're in, especially true if you're in inertial fusion energy conditions, but also in MFE. Chemical environment, it's coming from all sides. If you're in contact with a blanket, and that blanket is a liquid blanket, maybe a liquid blanket design or concept design, you're going to have highly corrosive molten salts in there. You have chemical issues associated with discharges of ions, namely hydrogen isotopes coming from the inside of the chamber. All kinds of things going on. Transmutation, whatever material you have there to begin with, it's going to change through transmutation. And I don't mean change minimally or marginally. It's going to change significantly. It's going to become a different alloy. And therefore, the properties for which you designed that alloy in the first place are going to change. So you have to contend with changing chemical composition, which leads to changing microstructure, which leads to changing properties during operation. You can't anymore rely on a zero-point design, as we say, on what the material properties are at the beginning. And then finally, you have issues associated with irradiation damage, which is you're really knocking atoms out of their equilibrium positions and creating a whole bunch of defects in there. And those defects are very complicated. I'll show you some examples. They're very weird. They behave in mysterious ways. It's taken us decades to understand them. We don't fully understand everything yet. But they control the fate of the material long-term, under long-term exposure. So all of these things are co-occurring in a fusion environment. And for that reason, not the only one, but for that reason, we can't say that we have a fusion material. They don't exist as of today. So when you hear all these exciting and novel concepts about fusion reactor designs, just think that they don't have materials yet for those. Okay, at least for they may have it for the first of a kind or maybe pilot plant, but no, we definitely don't have anything for next of a kind or commercial power plant. All right, so what are these challenges? Just sort of listed here in a bullet list type of way. We have plasma materials interactions. This is more specific to MFE, but some of these are applicable to IFE as well. So we have sputtering, redeposition, and tritium implantation and retention. Sputtering means the material is being eroded. The plasma phasing armor is being eroded away, right? That's bad enough, but all that erosion is actually, all that material that has been eroded becomes redeposited elsewhere in the reactor, right? So that now you have it where it shouldn't be, in amounts that are sometimes, we're talking about kilograms over years of operation. High heat fluxes in MFE, you're going to have, anywhere between 2 to 5 megawatts per meter squared in the standard chamber, equatorial plane of a standard MFE reactor. You're going to have up to 20 megawatts per meter squared in the diverter. And just to give you an idea, the heat flux that the space shuttle faces upon reentry, atmospheric reentry, it's 100 kilowatts per meter squared. So we're talking orders of magnitude relative to that. And as most of you probably know, those are extreme conditions already as it is, right? So we're talking an order of magnitude or more extreme situations here. You're going to have degradation of materials and structures. So these materials will lose their structural and dimensional stability due to fusion neutron exposure. Fusion neutrons they cap at 14 MeV, but they have a tail of lower energy neutrons. All of them can do damage in their own way. We talked about corrosive environments already. Large time varying thermomechanical stresses at high temperatures. We're not allowed to work with the full periodic table when we design fusion materials because we have a reduced activation mandate, which means that ideally, and I say ideally because I think these guidelines will have to be revised, but all fusion materials, specifically structural fusion materials, will have to be certified for shallow burial, so Class C waste disposal. and that means relatively low activation. So that limits the amount of elements that we can choose to design our alloys and materials. They have to be able to be resistant to air and water corrosion in case of a loss of coolant accident, air ingress into the reaction chamber. And of course, all of this is going to happen under operation, but they need to be able to harness fusion energy, right? So not store a lot of tritium in there. We have to be able to extract the tritium from the hot coolant and then mitigate thermohydraulic and magnetohydrodynamic instabilities in the case of MFE or strong X-ray and debris discharges in IFE. All right, that means basically that we have a very narrow design window. That's just what it means, okay? If you take into account chemistry, temperature, lifetime, which really means irradiation dose, we have a really narrow design space. So that's really forcing us to have a hand tied behind our back when we design these materials. This is what I was talking about the reduced activation mandate. So again, we can only work with certain elements, transition metal elements, specifically of the periodic table. We're limited by the impositions imposed by, or the imparted by these mandate. All right, this is my slide here that I wanted to introduce. So you're going to see this acronym a lot, DPA. It stands for displacements per atom. And you might think that it reflects how many times an atom has been displaced from its original position, but that's too simplified really for how these parameters define. So you should see it as a measure of how much energy is coming into a material through irradiation, okay? It's a more accurate description of that than an actual reflection of how many times an atom has been displaced. But if you can abstract and think of it that way, that's fine. It's basically how many times each lattice atom in a material has been displaced irreversibly from its original position. So 1 dPa means that every atom, on average, has been displaced from its original position. For fusion, you're going to see that some materials are exposed to hundreds of dPa, and that's just mind-boggling. Yeah?
Doesn't it matter how far it's displaced as well?
So 1 dPa assumes that it's been displaced far enough that it loses memory of where it came from already. So that's sort of embedded in there. Yeah, that's right. It's an irreversible displacement. Yeah.
Is it a time integrated quantity, or is it like a rate of per year?
It's time. It's basically time. It's
integrated over
yes.
a lifetime. Okay.
Yes, exactly.
And so when you say you should think of it as energy, is it essentially saying the energy scale you're using is like the potential that you have to overcome to displace the atom?
Pretty much. Pretty much. And the reason for that is that the meaning of dPa is not the same in a steel that it is in silicon carbide or in tungsten, so you can't really say that 1 dPa means that one atom has been displaced on average in the same way in different materials. But the energy that material has received is about the same if you have a given dPa.
And this is just for neutron damage or also radiation damage?
Any radiation, because it implies energetic particle irradiation leading to atomic displacement. So whatever the source of that displacement is captured by dPa. It's a legacy thing. Nuclear engineers going back to the 1950s love to use it, and the community has tried to convince them that we should change to something better. It's impossible. So we're just gonna adapt to them. And again, it's kind of funny in many ways because they're so stuck in their ways. But the problem is that the NRC, which is the regulatory body in the United States for certifying materials and things like that, is going to use what those nuclear engineers want them to use, and that's dPa. So we have to adapt to these formal guidelines so that we can speak the same language. So examples of that are here. You can see dPa's. You'll see them in the x-axis of all these charts. So this is how properties change with irradiation dose, which is the same as to say with time in a given nuclear environment. Okay, we don't have a fusion reactor where we can test materials. It doesn't exist yet. We don't actually have even a testing facility that mimics fusion conditions yet. We've tried to convince the Department of Energy for 3 decades. We always say, maybe, or, keep trying, maybe. Now it's more difficult because the private sector doesn't necessarily want that capital investment to go to a research facility. They want, they would prefer for that investment to come back to them in the form of technology development. But, we've been pushing for that, and it's sorely needed, I think. But anyway, so these are all tests that have been done either in fission reactors, some of them fast reactors. We don't have any fast reactor. Fast, I mean very high energy neutrons, similar to, not quite similar, but closer to what fusion neutrons would be. We don't have any in the United States at the moment. Russia has one. We can't use it. We haven't been able to use it for about 10 years for political reasons. Japan has one, which is up and down, decommissioned, and retrofitted, and so it's not highly available. So it's really difficult. Neutrons are really expensive, very, very expensive. In the United States, we have thermal neutron reactors, testing reactors. We have one in Idaho, one in Oak Ridge. But the time that it takes to accumulate DPAs is really, really slow, and the spectral effects really have an impact on how materials evolve. So they're not ideal. So people have done ion beam irradiations, which are very fast and cheap, and we have a bunch of those in the US. The issue with ion beams is that you don't get the transmutation that neutron irradiation gives you, so you have to induce it externally, and that's always complicated because you don't know if you're mimicking exactly what's happening. But anyway, just to give you an idea of the difficulties that we face when we really want to test fusion materials. All right, but here you see the strength of a family of steels. Here you see the fracture toughness as a function of those. So steels will harden with irradiation, which could be good, but that hardening comes at the expense of almost zero fracture toughness, meaning they become extremely brittle. Okay, and that's why I say that even some of the most advanced steels could not perform under nominal fusion conditions. Okay, we don't have a fusion material at the moment. Okay, the fracture toughness goes down, meaning it's going to behave like a highly brittle ceramic, steel. And we use steels because they're very tough, right? They don't break. Also, they swell, so they will literally swell. They will irreversibly, not like elastically, but they will increase their dimensions irreversibly, which means that when you're looking at really fine tolerances, when you're doing these designs, you can't have a material there that just swells by 15%, 20%, something like that, right? You can think of a large structure just increasing its size. So huge issues. The microstructure can change completely from going from equilibrium thermodynamics to non-equilibrium thermodynamics. Effectively, irradiation, what it does is it drives the system really far from equilibrium. We can't sometimes use these theories, standard thermodynamic theories, because they don't apply. But we see their effects in the microstructure of real materials. And again, it brings a whole bunch of issues with it. A huge issue for fusion, which sometimes I think is not fully appreciated, is that almost in every material, you will produce relatively large amounts of hydrogen and helium through transmutation, okay? Alpha particles and protons. These will become gaseous impurities, and as such, they will form bubbles. They will coat grain boundaries. They will go to precipitate interfaces, and effectively, they turn your materials into a sandy, grainy mess. And I mean it. That's one of the reasons that leads to their low fracture toughness. Helium will coat every grain boundary. The grains will lose consistency and coherence, and the whole thing will just kind of become a grainy, useless mess in your hands. Okay, so helium and hydrogen are huge issues. Hydrogen, we can control it chemically a little bit because it's reactive, so we can throw things in there that will trap it and form hydrides that we can more or less control. Generally not, but we can try. Helium doesn't react with anything. It's the second lightest element, but it's as big as iron in terms of atomic radii. So it really needs a lot of volume. It swells everything. It's very, very harmless or harmful. And again, we cannot. Usually, when you talk to a fusion materials specialist, they will always look at the helium production first. That's on top of anything else, because that's really what drives so many of these detrimental effects. Okay, but we don't really know the cross sections for helium production in many materials above 20 MeV. Okay, for fusion that's fine, more or less, although you can see that different nuclear data libraries diverge from that point on widely. But for some of the other testing facilities that we want to use that may have neutrons that are higher in energy, there are huge uncertainties. So in the 21st century, we don't really yet know how to deal with many of these things. Here you see the effects of helium, how they form these bubbles, and these bubbles will eventually coalesce and give you like a pillow, like a cushion between gray boundaries. And they will lose cohesiveness, and they will separate, and you'll have zero strength in these materials. All right. Enough bad news. Let's move on to something different. Okay, let's go to something a little bit more fundamental, theoretical. So, yes?
Just before you move on,
Yeah.
so this story of swelling, that's something that's unavoidable, right? I mean, do we know of any materials that would not swell, at least not significantly?
With helium in them, if you don't have helium, we know materials that will not swell under radiation. We can control the microstructure in ways that will prevent swelling. With the moment you put helium in there, it's unavoidable. It's physically, like you say, physically unavoidable, because the helium is, like I said, very large and produced in large quantities. Yeah, it just...
And the helium bubble creation cannot be avoided, right? So swelling cannot be avoided. Is that a fair statement?
Swelling cannot be avoided. Swelling cannot be avoided, but we can control right now how much swelling is produced for a given amount of helium, because we can tailor the microstructure in such a way that we prevent helium from aggregating in localized locations of the material. We call it helium management. So we can try to manage helium in such a way that minimizes swelling, but it cannot be avoided altogether.
You mentioned the 20, trying to get cross sections of 20 MeV, but where would that come from? It's like the neutrons or the 14.1. So like, where would you get like 20 MeV?
Where would you get neutrons that are that energy or higher, or how would you calculate those? How would you?
Like in a fusion reactor, like where would there be?
So in a fusion reactor, you'll never have it because they're capped at 14 MeV. But we have been trying, like as I said in the beginning, we've been trying to push for a materials testing facility, which will not be a fusion reactor, but will be a surrogate. And these surrogates almost always have neutron energies that are higher than 20 MeV. They have a high energy tail that decays fast, and you could say, okay, we're not going to have an infusion, so we don't need to worry about it. But what we do is we test and validate the models against those surrogate facilities, and then we bring them over. So we need to make sure that we capture what's going on in there. Another example is a spallation neutron source, which can get up to 600 MeV. Again, not a huge flux, but 600 MeV neutrons. So, and we don't really know how to calculate, or we don't have data for these cross sections.
But the helium bubble creation, I mean, that's all based on simulations, or?
No. These are.
Yeah, but under fusion power plant conditions, I mean, no one knows, right?
Yeah, no one knows. These are like emulated conditions. Yeah, experiments with similar. So I'm going to show you later how we try to design experiments where the ratio of displacements to helium production is the same as in a fusion reactor, right? And we inject helium at the same time as we inject displacements, and we see their coevolution, as you would have presumably you would have in a fusion reactor.
So can I ask one more question?
Yeah.
Sorry.
No, please. Yeah.
So you say the high production of hydrogen and helium is unavoidable, but that's a nuclear reaction from the 14 MeV neutron going into the material. I wonder, can you choose a material so there's just not a nuclear reaction that produces
Right.
helium?
Yes. So
Or is that just
I like how you're thinking, because this is how we started thinking 30 years ago. No, it's very good. The helium and hydrogen are produced through threshold reactions, and the threshold is about, in steels, is about 2 to 5 MeV. You will start producing helium and hydrogen above that. So we never had these in thermal fission reactors because the energies are always lower. So for the materials where that threshold is pushed above 10 MeV, and ideally 14 MeV, those materials are not really of any use. So doing what you say, which is, again, the right way to think about it, doesn't really help us much. We can introduce precipitates there and fibers and make composites that play with that notion, but it's not the final solution, I would say. No. All right. Okay, so like I said, enough with the bad news. Let's move on to the models. Okay, what is the main challenge? I'm going to show you this chart, but the main challenge about irradiation in general, and nuclear materials in general, but fusion specifically, is that everything starts with the impact of a neutron with a lattice atom. And that's something that happens at length scales of angstroms, 10 to the minus 10 meters, and time scales of femtoseconds, 10 to the minus 15 seconds, okay? So everything starts there, but the effects are felt at the engineering scale. We see swelling, we see helium accumulation, and we see embrittlement and fracture toughness going to zero and hardening and stuff. Things that we can measure with a tabletop device. So we're basically saying that we have to bridge, approximately 20 orders of magnitude in time and slightly less in length to be able to project what happens at the atomic scale with what happens at the engineering scale. That's an insane challenge. I mean, it's a grand challenge of incredible proportions, okay? Because unfortunately, we have really good theories for what happens here. It's called quantum mechanics, or it's numerical implementation, which is density functional theory. And we have very good, and by the way, there's a whole bunch of commercial codes that are based on density functional theory. And I always say when you have a commercial code is that no one questions the underlying theory, right? Because people use it. We have good theories for the macroscopic scale, mean field theory, okay? Where volume and time averaging works well. And we have finite element codes that can play with that, right, to simulate materials behavior or component behavior. Again, a whole bunch of commercial codes. No one questions that. We have no theory in between. And I mean it. There's no formal theory in between. Quantum mechanics, of course, it doesn't break down, but it's impractical to use above the Debye limit, let's say. And the mean field approximation breaks down when you have fluctuations and things like that in between. So we have no theory. We can try to bridge. So this has become a multiscale paradigm in which we have to develop mathematical tools at each one of these scales. No one is telling you which ones are more prevalent. You have to, through experiments and through intuition and through, experience, you have to be able to detect or predict which scales are going to be more relevant, what processes are going to be more relevant. So this is almost an art, still today, as much as it is a science, which I'm happy to say is good in the age of AI, because I think AI is not very artistic yet. but we'll get there. So anyway, so that's what the community has done. We have no theory, but we have a set of best practices when it comes to developing different methods, linking them together, knowing what information should be passed, what information doesn't need to be passed, simplifying the linkage, and hopefully be able to get from the electronic structure all the way to the macroscopic scale. So that's the context for method development that we have to work within. Again, very challenging. Nuclear materials are not unique to this. This happens in many other fields of science. But I would say, at least I haven't seen, and I'm a little biased, but I haven't seen a challenge of this proportion in terms of multi-scale model. But if someone wants to dispute that, we can talk about it. Okay. The other thing is that because we don't really have fusion reactors yet or fusion testing facilities yet, we are tempted or biased to place a naive faith in multi-scale modeling sometimes. Okay, especially when you talk to people that are outside the field, they say, "Oh yeah, you just model everything. You know, now we can do video games, we can do all kinds of things." And you'll hear things like, "Modeling is the future. You know, the experiments can only tell you so much. They're dirty. They're expensive. You just don't need to assume anything anymore. Just simulate it from the laws of quantum mechanics. Computing power will forever increase, right? Moore's law. You know, we can simulate electrons and ions all the way to the macro scale. AI, if we miss any of these, AI will solve everything, and we will be able to certify materials just with modeling." And I'm happy to see you guys laughing because wrong, nope, wrong, yes, laugh. Okay, not even close in any of these. Okay, this is not going to happen. Okay, unfortunately. So, all right. Let me introduce the mathematical formulation of irradiation damage accumulation, which I said it's a small part of the overall theory. It's not the overall theory. It's just one of the theories that we use for this. All right. So what we're going to do is this. We're going to assume that we have a chemical reactor, basically. We're going to use chemical reaction kinetics. We're going to assume that there's an external source of reactants, which is irradiation. You know, you have neutrons or high energy particles coming in. They're producing a bunch of species. They're not really chemical species. They're structural species like defects, vacancies, self-interstitials. Through transmutation, you may introduce new chemical species as well. Okay, and now those species are all reacting with one another. Everybody with everybody, okay? And they're reacting with the microstructure, and they're subjected to the boundary conditions, just like a standard chemical reactor. All right, so you can write that, you know, generalized advection diffusion equation, or, you know, this is a derivation of a Fokker-Planck equation, you know, and it has your standard Fickian term. I think I have this highlighted as I go. Oh, I can do this. Right, so that's Fickian diffusion, and that depends on the crystal structure and the chemistry and things like that. You have irradiation proper, which is you're inserting defects in there, and that depends on the irradiation conditions. So fusion is going to be different than fission, different than ion beams, different than electrons, all that stuff. Here you have all these defects that are being created are now interacting with the microstructure. They're going to grain boundaries like the helium does. They are going to free surfaces. They are going to dislocations, precipitates, whatever you have in there, the defects will find and will interact with. And then finally, you have reaction kinetics. And reaction kinetics is generally is truncated at second order, like you see here. But in some cases, especially IFE, for example, inertial fusion energy, where you have these super intense discharges of neutrons, the doses may be so high in such a short time that you can't cap this at second order. You have to go to third order, meaning you'll have 3 species reacting at the same time. Okay, so even this is a simplification in some cases. Okay, and this is materials physics. All right. It's taken the community a couple decades to identify each one of these terms physically, like through experimentation, through density functional theory calculations. Like each one of these takes a long time because diffusion theory is a field in its own right. Irradiation damage is, I can't even tell you like how long this has taken. It's still going on. Microstructural evolution and reaction kinetics. Like each one of these is a challenge in its own right. But now you put it all together and this conforms a system of millions of equations, strongly coupled differential equations, PDEs, right? Because you have to write an equation for each defect species. And each defect species is represented by a cluster with a given number of defects. You may have a mono vacancy, but you may have a divacancy, and you may have a trivacancy and a tetravacancy, and you go down the list until a vacancy cluster that has 100,000 vacancies, like a bubble. A bubble has 100,000 vacancies or more. So you have 100,000 equations for the vacancies. And likewise, you'll have 100,000 equations for the self-interstitials that used to occupy those vacancies. But every self-interstitial cluster can interact with every vacancy cluster. So now you have 100,000 times 100,000, 10 to the 10. And now you throw helium in there. And helium can interact with all the vacancies and all the interstitials, and helium can form clusters themselves. So you're looking at, forget about the 6 there. I was trying to not discourage the students, but it's more like 12 there. Okay? So this is, again, just to look at the fate of all the defect species that you have in there through radiation is a monumental challenge. I mean, it's just crazy, right? Because the number of equations that you have. And we have had really smart applied mathematicians that have helped us with the formulation of this equation system. So we have tricks that we can do. We can do grouping methods. We can use stiff linear solvers. We can do a whole bunch of things to help us with this, but still a huge challenge. Okay? All right, so this is like a typical diagram of how we couple different codes going from neutronics. Again, the theory of neutron transport itself it's a field, a legitimate scientific field, right? So just that alone is, requires significant resources and investment and things like that. Then we have to translate the neutron fluxes into damage production inside a given material, and then the defects that damage produces has to be characterized in terms of what the structure is, what they do, how they interact with other defects, and then we have to elevate that and see how the collective kinetics of all those defect species leads to cluster evolution and buildup and helium. Anyway, you get the picture. All right, so here you see the result of neutronics calculations. So you see the neutron fluxes that you are to expect in different fusion, MFE fusion designs. Okay, so this is a helium-cooled lithium-lead, helium-cooled pebble bed, water-cooled lithium-lead, water-cooled ceramic breeder. I mean, there's different concepts that are being, thrown out there. This is the standard fission reactor, pressurized water reactor, and this is the high-fed reactor, the experimental reactor at Oak Ridge that we use as a testing facility. Of course, none of those have the peak at 14 MeV, but anyway, you can see here sort of how these neutrons go. If instead of using neutrons, you're using ions, well, we have codes that help us characterize how much damage these ions will produce as a function of depth. Ions are subject, especially heavy ions, to strong Coulombic interactions. They're not going to penetrate deep, unlike neutrons in a material. So you have to take into account the near surface effects and deconvolve those so that you can map or match what you get in an ion beam experiment to what you get in a neutron experiment. Again, very challenging. We can co-implant helium, hydrogen, and damage in such ways that the ratios between the three reflect what a presumed fusion reactor would have. So we can do all these things. Okay, we use sort of elementary theories like the Kinchin peace model for damage production. We have codes for that. We create energy distributions of primary knock-on atom species. These are the atoms that receive the neutron impact directly, okay, primary, or the ion directly. And we can see how neutron or ion energies translate into internal lattice atom energy distribution. So we can do that. And I'm going fast. There's many details behind this, but you don't need to worry about that. All right, defects. Defects are weird. When I show these to some of the students, I have to tell them this is not a biological system. This is a solid state, metal. It's just like a metal. And I have to convince them that these are not like, ladybugs or wood ticks or something moving in there. But you can see these are crystalline defects at relatively high temperature, and you can see how they move. They move in 1 dimensions, in a 3-dimensional setting, but they move in 1 dimensions. Some move, some don't move. Some look like a coffee bean. Some look like a bug, like I said, like a little black dot. So again, just understanding what's going on here is challenging because this determines the kinetics of the defects, how they interact with one another. So that we've had very smart physicists help us interpret this. Now we know that these form disks, and these disks move preferentially along their glide cylinder, as we call it. They're trapped in their cylinder and they can move in 1 dimension like that. But some others don't form disks. They form these other more quasi 3-dimensional structures and they can't move. So we have to take all this into account in the models to be able to faithfully simulate what's going on. Okay, how do we do that? Well, now that we know, more or less, how damage is being produced inside the material, we have to characterize these defects. So the method of choice for the last 20 years has been density functional theory, so ab initio methods. So they're highly attractive, especially for computational physicists or computational material scientists, because the promise is that they will allow you to simulate everything without empiricism. By providing solutions to the corresponding Schrodinger equations. By the way, time-dependent Schrodinger equations, because you have electrons going in there and particles moving in there. The numerical implementation, the practical numerical implementation, as I said, is density functional theory. But just to go from pure quantum mechanics to density functional theory, there's a bunch of assumptions that you have to make that really don't make DFT ab initio, I would say. Okay, so we have to make assumptions, approximations, and there's some degree of empiricism. Yet, even there's holes in the theory, even, that we don't know. Like the many-body problem. As far as I know, that hasn't been solved. And right now, we still employ a process of trial and error to see how to deal with a many-body electron problem. Okay, but in density functional theory, effectively what you do is you write your time-dependent Schrodinger equation, which of course cannot be solved exactly or numerically, except for the hydrogen atom. So we have to resort to approximations like the Born-Oppenheimer approximation. We have to resort to the description of the exchange correlation potential, which again, we're not 100% about. Okay, so anyway, you can read what's here, but the main point is that density functional theory, while incredibly helpful for many things, is not without approximations, number one. And in irradiation damage, we're pushing the limit of what DFT can do. And also, despite great progress in computational power and algorithm developments, it's still hard to get really outside that angstrom nanometer femtosecond scale. It's just difficult to push through that barrier, okay? So we haven't been able to really elevate this to scales that are not just confined to the atomic scale. Okay? All right, so like I said, they've been crucial in predicting the structure and the properties of some idealized systems, like some of these defect structures that I was talking about, but No, they're not the final solution. They're not the ultimate solution. We then have to say, okay, let's go to something that is more efficient, like classical molecular dynamics. Okay, solve essentially Newton's equations of motion, generalize Newton's equations of motion within Hamiltonian mechanics, and try to push the envelope of the time and length scales that can be simulated. All right, so we do that, and these require something known as force fields, which is the gradient of the potential energy functional. And these force fields often come from DFT calculations, so there's a linkage there. There are machine learning approaches that are really helping us make progress in terms of these force fields. Okay, one nice thing about molecular dynamics is that it's highly scalable computationally, mostly because we have been able to come up with approximations that are short-ranged, so we can reduce the n-squared problem to a n log n type problem. Okay, sometimes even like a quasi-linear, with n problem. So that makes them very, very nicely scalable. You can use massively parallel calculations to do these things. And you can calculate ensemble averages, you can calculate time-dependent properties, you can use Green-Kubo theory and get things like the diffusion coefficient, the thermal conductivity, the viscosity, etc. of many materials. And they have allowed us to study, if I can play this, processes like this. This is the impact of a neutron on an atom, right there somewhere. And then that atom, which is known as the pKa atom, the primary knock-on atom, as I said, goes on to produce a cascade of displacements. And what you see here in red are vacancies. So lattice sites that used to be occupied, that are no longer occupied, they're vacant. And what you see in green are the atoms that are in no man's land. They're self-interstitials. They used to be occupying a lattice site, and now they're found roaming around. They have no place to go. And that reaches a spike, and then everything kind of cools, as heat dissipates, everything cools down. But some of these interstitials cannot find where they came from. They cannot recombine back to where they were. And what you have at the end is a remnant structure with vacancies and self-interstitial atoms. But as you can see, some self-interstitials are isolated, some are forming large loops, the vacancies are forming linear chains, or they're isolated. So anyway, very complicated, they behave in very mysterious ways, and it's just hard. Okay, here you see two still shots of that. All right, the other thing is that we can look at an experiment right now using molecular dynamics. That's what that is. And we can simulate the equivalent structures, what we think are the underlying structures that you're seeing there, like that horse hoof thing or coffee bean thing. We can simulate it, and then we can say, oh, okay, the match between that experimental image and that simulated structure is good enough, qualitatively actually. So we think with a given level of certainty that what we're seeing in the experimental micrographs corresponds to some certain atomistic structure. We go back and forth, and we can characterize these things. Okay?
In these simulations, if you go back to the previous slide,
Yeah.
there must be far fewer atoms in the simulation than the actual material. So how can you say that they're...
Yeah, you're right. You're absolutely right. Right? These are, the scale doesn't show here, but this is like 50 nanometers. And these are probably 1 to 2 nanometer simulations. Yeah, which still have hundreds of thousands of atoms. Yeah, so we have to really cut that out, like isolate any one of these structures that you see here and simulate them separately. So we like divide and conquer type of thing, with this. So again, the approach is not infallible, it's not perfect, but at least qualitatively we can say some things about these defect structures using molecular dynamics. Okay, all right, I'm gonna cut to this one. Even molecular dynamics is not efficient enough to push you beyond the, let's call it the microsecond is really pushing it. Really hundreds of nanoseconds and maybe tenths of a micron. Okay, you're still looking at something extremely small. So we can continue up this, escalation ladder, this multiscale hierarchy, and we can use Monte Carlo methods, specifically kinetic Monte Carlo methods, in which instead of simulating every atom, now you simulate processes. Okay, and you use the resident time algorithm to simulate events taking place at the right probability. And then what we use molecular dynamics for, or atomistics for, is to characterize the physical constants that govern the event rates that you have. Okay, and with this, you can then achieve or push the envelope of length and time scales that you can achieve. Okay, so you see here. And with that, you can now simulate, instead of one single cascade, one single impact, now you can simulate many using Monte Carlo methods, right? You can see how, these things pop all over the place. So what I showed you with the molecular dynamic simulation would be one of these, just one of those, right? And now we can simulate a bunch of them. And that allows us to push the DPA scale to not just 10 to the minus 5 or 10 to the minus 6, but now to 10 to the 0, maybe, or 10 to the 1.
Question.
Yeah.
How do you calculate the rates and probabilities for use in multi-scale?
So for example, and as I show you in that experimental image, there's so many different complicated mechanisms that you have to try to capture all of those and implement all of those in terms of rates. So for example, one thing we'll do is we will put a defect disk, one of these clusters that I was talking about, we'll put it in an atomistic box. We'll simulate the kinetics of that disk at a set of different temperatures, and from there we will extract its diffusivity. And then we get that diffusivity, we put it in a kinetic Monte Carlo code, and then we see how, when those defects are produced, we can expect what the final outcome of the collective diffusivity of those defects will be.
Very cool. That's really like multi-fidelity. So you get like the rates from like your DFT simulation.
Exactly.
Okay.
From the lower scale, higher resolution model. And we use it in the right way, which is for that, instead of simulating the whole thing, which we can do. All right. And then another thing is the defects are not just there by themselves. Like I said, they're interacting with the microstructure. Microstructure can be anything in a material. It can be grain boundaries, dislocations. Dislocations are these lines that you see here. And every material has this, any real material has dislocations. So there are these lines that you see here, and you see how in this in situ irradiation experiment, the dislocation interacts with all of these defects. And the defects are moving as the dislocation is moving. And the question is, what is going on, right? What sort of processes are taking place here? So again, we have to go and simulate these things. And for that, we use yet another technique, which is based on elasticity theory. So now we're looking at long-range simulations, right? And elasticity theory gives you a pretty good representation of how dislocations move. Again, if you've never heard of dislocations outside, the medical field, they're just line defects that control how a material deforms, plastically deforms. Okay, but we have techniques that can do that. They can piecewise discretize the dislocation lines, right? And then we use the laws of elasticity to capture their interactions. The issue, we call this dislocation dynamics, and we create images like this, where you have like a forest of dislocations. And this is an image that was created by my colleagues at Livermore when I was there, using a highly parallel code that can now simulate tens of millions of these segments, okay? Which is now pushing the length scale to the micron level. Okay, so a micron is, what is it, 100th of a hair thickness or something? So, we're getting there. Okay, so we can do these things. The issue with dislocation dynamics is that it's also an n-squared problem, but it's a long-range problem. So it's much more difficult to scale up computation. Okay, so, and this is why only the computational resources that are available at national labs are, well, let's say not only, but they're better suited for this type of code implementations because they can be run there. Okay, so anyway, I'll show you some of the things we can do with dislocation dynamics. I'll run quickly through this. We can simulate how these weird structures form and interact with dislocations. Okay, and this tetrahedron that you see here, you would think that's just like a movie, like a cartoon, like a joke, right? Like something. But no, they form under radiation. You can see them very nicely under radiation. And thankfully we know why, but you can see them in real materials, these tetrahedra. So they exist. It's weird. It's like this mystery of, when you radiate something, sometimes you never know what you're going to see. But they exist. They're there. We know how they form, so we can simulate them. And then we can elevate this into large-scale simulations with many of these defects and many dislocations, and then we can see what the effect is. Okay? And if you filter simulations like that through another algorithm, you'll see that these dislocations form channels. Eventually, they will form channels. So these locations are blue, and the defects are green, yellowish. And you can see that these locations eventually form channels, which they form under radiation. You see the channels under radiation forming. So we can make progress. I mean, we're making progress. We understand the physics of radiation much better. Still many challenges facing. Okay. All right. The other thing I want to show you is, and I have two more brief examples, and then we'll wrap it up. But is that when these loops that are formed through neutron radiation, when you let them anneal at high temperature, and again, in a fusion reactor, the temperature is going to be, you're going to push the temperature envelope as high as you can because you want the thermal efficiency to be as high as you can. And the higher the temperature, the higher the thermal efficiency. So we have to know what's going to happen to these materials as they are irradiated at high temperature. And you can see that then these loops start to coalesce. Right? You have loops that start to grow first, and then you'll see how they coalesce. They form elongated structures that form like these ribbons and these loops and stuff like that, like very long loops. So now they're growing and coalescing with one another. And you can see their effects here and in different experiments at high temperature. So again, we wanted to understand how they do this. And the way these loops coalesce is by absorbing defects. So now we have to, but the loops are, I'm throwing a whole bunch of things at you, but please don't mind me. The loops are dislocation lines which produce an elastic deformation field. So the defects surrounding the loops are feeling an elastic deformation field. They're not just moving, kind of neutrally. So we have to implement that, capture that in the theory. And again, a lot of detail here, but if anyone is interested, we can discuss that later. But we put that in the theory, and then we see how these loops interact with lines. And hopefully, and as the loops interact with the lines start to climb. They go up, they go down. Here you see vacancies kind of diffusing in the stress field of the dislocation. And we have to capture that through appropriate corrections to the diffusion equations. And the lines start to climb. And these are lines that are discrete, so they form like these discrete steps in there. We can play with those. And these are nice simulations because you see how the defects move in response to the stress field. They don't move neutrally. Now they follow prescribed paths, diffusion paths, in response to the stress field created by these defects. So irradiation is producing single defects, and temperature is making some of the defects coalesce into large loops. And now the two are interacting with one another in this sort of non-trivial way. Okay, but if you're, lucky enough, you can then put it all into a simulation model based on dislocation dynamics, and you can see how we can capture what happens in the experiment. Like these loops are growing by absorption of these mono vacancies, and they touch and coalesce, at least qualitatively similarly to what you would see in the experiments. Okay. All right, and to conclude then, I say, okay, what about so we know that we have these loops, we know that we have all these defects, we know that we have channels forming when there are dislocations in there. Can we say something about the macroscopic scale? Let me see if I can bring this up to the macroscopic scale. And in a real material, we'll have grain boundaries, right? We don't have single crystals. We have a material with many grain boundaries. So now we put it all together into a finite element code. with information transfer from all the lower scales along the lines of what I've been showing you throughout the presentation. And now you can see how as we deform this polycrystalline system, bands form. So what you see there in shaded, the shading tone represents the formation. And the formation actually proceeds initially through localized bands, just like it happens in the experiment. And I'll cut to the chase here. So if we don't have irradiation, right, there's no bands. This is a stress-strain curve for an unirradiated system. And you deform it uniaxially, like you apply tensile load like this, and the system deforms. And there's some discreticity here because you have grains, and the grains are oriented differently and all that. But more or less homogeneous deformation as reflected by this sort of monotonically increasing stress-strain curve. But when you irradiate the system, you find two things. The first one is now you don't have monotonic increases. You have a sharp hardening, and then you yield. The system deforms, starts deforming. You have softening, so the stress drops, and then it goes back to what it should be. And that peak and that drop are associated with the formation of these bands, right, that we can capture in the models. And if you look at the experiments, you'll see that, indeed, when you don't irradiate, you have sort of the standard monotonically increasing curve. Don't worry about the drop here. The drops are when the system fractures and breaks, but all the way to the top. But when you irradiate it, you have a sharp increase in strength and then a softening associated with the formation of these bands. So we can capture them in finite element codes informed by defect physics going all the way down to the atomic scale through the linkage of all these methods that I've been discussing to you. All right, so we'll wrap it up there. And just two main, you don't have to read that. Two main thoughts. First one is the boundary conditions and the physical, mechanical, and thermodynamic impositions on fusion materials is mind-boggling. No surprise there. Okay. Okay, let's test the materials under fusion conditions. We don't have a testing facility for fusion conditions. Okay. All right, let's then build models, at least to learn something, to be able to simulate what happens. Okay, but this is a multi-scale challenge, so it's extremely challenging, difficult to do it. But we do it, we try, and this effort started in the 1950s, sort of on the heels of the nuclear nuclear energy initiation. And finally, with the combination of multidisciplinary science, advanced algorithms, computational power, as of late, AI aided physical improvements, and a whole lot of intuition, luck, failures, frustration, successes, we can now put methodologies together that are getting us closer to understanding what will happen in a fusion environment. So that's really what I wanted to transmit to you, and yeah, we'll leave it there. If there's any questions. Thank you.